Your phone, your computer, and even huge power systems rely on capacitors every day. But how can two metal plates store energy? Your phone, your computer, and even huge power systems use capacitors every day. But inside these devices still something surprisingly simple. Two metal plates separated by a tiny gap. Somehow, the tiny structure can collect and release energy whenever it is needed. How does something that simple actually store energy? Today we are going to follow the process step by step and see what is really happening. A capacitor has a very simple structure. It contains two conductive plates separated by an insulating material called a dielectric. Plates never physically touch each other, and that separation is extremely important. Without the gap, electrons would immediately move between both sides and nothing useful could be stored inside the device. The entire behavior of the capacitor depends on this simple arrangement. If the plates touched directly, the extra electrons would instantly spread out and balance themselves. There would be no separated charge and no electric field between the plates. The capacitor would simply behave like a normal conductor. The tiny space between the plates is therefore no small detail. It is the reason the capacitor works at all and makes energy store possible. Everything depends on that separation. Now imagine connecting a battery to the capacitor. The battery begins pushing electrons toward one plate while pulling electrons away from the opposite plate. One side gradually becomes negatively charged while the other becomes positively charged. The battery continuously forces more charge separation into the system. At this stage, an important process has only just started. The system is beginning to change. The interesting part is that electrons do not jump across the dielectric material between the plates. Instead, charge starts building up on opposite side of the gap. More and more charge becomes separated as the battery continues working. The capacitor begins creating an organized electrical system, rather than simply collecting electrons in one location. This separation becomes the foundation for everything else. As separated charge increases, something invisible begins forming between the plates. An electric field fills the entire space inside the capacitor. You can think of the electric field as a region where electrical forces exist. Even so, we cannot see it directly, it creates very real effects and influences how charges behave. The field becomes stronger as more charges continue accumulating, and the field keeps getting stronger. Many people imagine that the capacitor stores energy directly inside the metal plates because the charge appears there. That sounds reasonable at first, but it's not really correct. The plates mainly provide a place where charge can collect and remain separated. The actual energy is stored in the electric field that exists between the plates. The metal plates themselves are only part of a much larger process. Something more important is happening. To understand where the energy goes, imagine stretching a spring. When you pull the spring farther and farther, you must apply increasing force against the spring resistance. The work you perform does not disappear. Instead, the system stores that work as potential energy which can be later released. The more effort required, the more energy becomes stored inside the system. Energy builds up gradually over time. A capacitor behaves in a surprisingly similar way. As more electrons arrive, the growing electric field begins pushing back against additional coming charge. Early electrons are easy to move onto the plate, but later electrons become harder to place there because the opposing force keeps increasing. The battery must work harder and harder as charging continues. The process becomes increasingly difficult. The battery therefore cannot simply dump charge into the capacitor without effort. It must continuously perform work against the growing electric field. That work becomes stored energy. The stronger the electric field becomes, the more energy exists within the space between the capacitor plates. Energy is not appearing from nowhere, it's being transferred into the system. The battery supplies that energy. Scientists describe the stored energy using an equation. Stored energy equals 1/2 multiplied by capacitance multiplied by voltage squared. One detail matters a lot here. Voltage is squared. That means changes in voltage can create much larger changes in stored energy. A small increase in voltage can produce a surprisingly large increases in stored energy. This idea becomes extremely important in real systems. If the voltage doubles, stored energy does not simply become twice as large. Instead, it becomes 4 times larger. Increase voltage 3 times, and the stored energy becomes 9 times larger. Small changes can therefore create surprisingly large differences in energy store capability. This idea explains why voltage becomes extremely important in capacitor design. Tiny changes can matter greatly. Capacitance also affects how much energy can be stored. Larger plates can hold more separated charge. Smaller distances between plates can increase interactions between charges. The dielectric material also changes how the electric field behaves inside the capacitor and influences overall performance. Engineers carefully adjust these properties when designing different capacitors. Every design choice changes behavior. Different capacitor designs exist because different applications require different behavior. Tiny capacitors may stabilize signals inside electronic circuits. Larger capacitors can have smooth power supplies. Supercapacitors can store much larger amounts of energy and deliver that energy very quickly when needed. Different jobs require different balances between size, speed, and storage ability. That is why capacitors appear almost everywhere in modern technology.